I'm Owen Garot, the scientist pilot on the second manned Skylab flight. During the 3 missions of Skylab in 1973 and 1974, fellow crewmen and I were able to demonstrate several of the fundamental laws of nature in ways not possible here on Earth. Skylab gave us the really rare opportunity to conduct these demonstrations in an environment which gravity was really not a factor. Ed Gibson spins faster with arms in, just as an ice skater does. Ed also tumbles faster after he tucks his legs in. These changes in angular velocity are illustrations of the law of conservation of angular momentum. A rotating body's angular momentum is the product of its inertia and its angular velocity. And that's what I've got shown for you on this particular line here. L, the angular momentum, is equal to the product of inertia and its angular velocity. The moment of inertia is a measure of a body's resistance to rotation, just as mass is a measure of a body's resistance to linear acceleration. The moment of inertia about an axis of rotation depends on the body's mass and on the distance of that mass from the axis of rotation. When the body's mass is located near the hub of a wheel, we can see that it is relatively easy to set the wheel in rotation. Therefore, its moment of inertia, or resistance to rotation, is relatively small. However, when the mass is located further away from the hub, it is more difficult to rotate the wheel. We may say that its moment of inertia has been increased. When we combine these two images, we see that the wheel with the lower moment of inertia rotates more rapidly, while the wheel with the larger moment of inertia spins more slowly. In simple cases, conservation of angular momentum means that the product of moment of inertia and speed of rotation remains a constant. When the skater pulls in her arms, her moment of inertia decreases because some of her mass gets closer to her rotation axis. Her angular velocity must then increase in order to keep her angular momentum the same. Now, some other demonstrations of the same conservation law. The same action in slow motion. Here Ed Gibson is twisting his upper body in the opposite direction from his legs. Since his initial angular momentum was 0, he cannot acquire any overall angular momentum. Here is Joe Kerwin demonstrating the same principle. An interesting example of a body with 0 angular momentum here on Earth can be provided by an ordinary house cat. Did you ever wonder why a cat dropped with 0 angular momentum can always land on its feet, even when it's dropped with its back facing toward the ground? Well, that's what we're going to show you now. This is our own cat, Calico, belongs to my daughter, and what we're going to do is to drop her upside down to begin with, allow her to land on her feet, and then play it back for you in slow motion. so that you can see exactly how Calico performs this feat. In always landing on its feet, a cat maintains zero angular momentum by twisting the front and rear parts of its body in opposite directions, somewhat as Ed Gibson did. Actually, the movements appear more complicated, involving rotations about several axes. A rotating body may be affected by conservation of energy as well as angular momentum. As you have probably already learned, when energy is transformed from one form to another, its total amount is conserved. Nothing is lost. Now, energy exists in a variety of forms, including potential, kinetic, and heat energy. Potential energy is defined as a body's capacity to do work by virtue of its position in space, whereas kinetic energy is contained in a body's motion through space. We learned an important lesson from this Explorer 1 satellite, which launched our whole space program back in 1958, just a few months after the Russians put up Sputnik 1. Explorer 1 reminded us that when a rotating body is not completely rigid, its kinetic energy can be easily transformed into heat energy. This can have surprising consequences. Explorer 1, and that's a model of it that I have here in my hand, it had a long cylindrical shape, and it was designed to spin about its longitudinal axis, just as it's doing here on the launch pad. It had 4 antennas at 90 degrees from each other, and here you see them before Explorer 1 was mounted on top of its rocket. Once in orbit, the antennas were designed to deploy like this. Now, scientists were very surprised after the initial elation over the successful launch of Explorer 1 to learn that the spinning satellite was beginning to tumble end over end. At first, the scientists were at a loss to explain this unexpected phenomenon. But after a week or so, they had solved the mystery. Now, they found that the reason that this had happened was that energy was being transformed into heat energy by the flexing of these antennas that were located around the midsection of the satellite. The heat energy that had been generated gradually lessened the angular velocity, although still, we must remember, the total angular momentum had to be conserved. Now, this required that the satellite change its spin direction, so that instead of spinning about this longitudinal axis, it had to be spinning or rotating about an axis which had a larger moment of inertia. And that, in effect, was what Explorer 1 had begun to do. Now let's look at another demonstration of that same phenomenon, using this time a drink dispenser from Skylab. Now, for this demonstration, I partially filled a dispenser with an orange drink so as to allow for a little turbulence to occur when it was rotated. Then, after I spun it along its long axis, the turbulence caused the kinetic energy to be transformed into heat energy, just as in the case of the antennas for Explorer 1. Now then, let's observe the videotaped results of the Skylab demonstration.
Now, we know that the minimum inertia axis of a long cylinder like this is along the axis of the cylinder. And the maximum inertia axes are either of the orthogonal axes, and it was found that if a body is spun about its minimum inertia axis, it will not stay spinning in that direction. If there's any energy loss mechanism available at all, it'll gradually lose a little bit of its energy and not only slow down its spin rate, but also begin to tumble until it finally stabilizes, spinning or tumbling about one of its maximum inertia axes. And that's the first thing that I'd like to demonstrate here. And this is much like our Explorer satellite looked some 15 years ago now. It may take me a couple of times to get it spinning just right. Then I'll want to get it spinning. There's a pretty good one. And I'll blow on it just to keep it in the field of view here. very gently, and now it's just about stopped. And you can now begin to see that as it loses a little bit of energy, because I've got some water bubbles inside here, that sloshing around of the water inside will gradually absorb just a little bit of energy. And you can see now how this drinking device is beginning to tumble just a little bit. It's beginning to precess and spin, and not about its longitudinal axis where we started, but instead about an axis just slightly off to one side. I'm blowing just very gently right about the center of mass so as to not disturb it if I can. And now it's just about to do that. We'll give it a few more minutes here. I've done such a good job of spinning it precisely that it's going to take quite a while for the energy to be absorbed. Just a very gentle breath is all that's required to keep it floating and stable. But now you see it's almost converted to a tumble. Very little spinning, almost none of it about its longitudinal axis, or the minimum inertia axis that I was describing a minute ago. I have to blow it back down into the middle of our picture here. Okay, perhaps that's enough. Now you can see that all of the energy that it had in excess available has been lost. Water rushing around on the inside, and it has slowed its tumble down so that the momentum has remained the same. Now, if you'd calculate the amount of momentum that it had in it to begin with and the amount that it has now, the angular momentum should be the same. But the energy has been reduced until it is just sufficient to give it this angular momentum.
Now that we've seen both the Explorer and Skylab demonstrations, let's analyze for just a moment the equations that explain precisely what it was that's happened. Now, this is, of course, the equation we've been working with. Total energy equal the sum of kinetic, potential, and heat energies. The kinetic energy can be expressed, if we like, as 1/2 moment of inertia times its angular velocity squared, potential energy, and then Q is just the symbol I've used for the heat energy involved. Now, we also know that the angular momentum, L, can be expressed as the moment of inertia times the angular velocity, and then this inserted back up into the equation for kinetic energy, if we should wish to, giving us with this final equation, which I want to talk about for a moment. The total energy equal the sum of these three terms. Now, we know from the laws that we've just been looking at that the total energy in the system must have been conserved and therefore held a constant. Also, the total potential energy did not change because the bodies that we were looking at, both our drinking dispenser and the Explorer satellite in orbit, maintained their same relative position above the surface of the Earth so that the potential energy was not changing. And then finally, our other law told us that the angular momentum did not change during this time. So the only thing that has been left to vary during the course of this changing and rotation is the amount of heat and the angular velocity. Well, now we know that as long as there is any turbulence, as there was, for example, in the drink dispenser and with the flopping antennas, the heat energy is going to increase during the time it was rotating. So that term had to increase. And the only way that this equation can be maintained in balance, then, is for the angular velocity omega to have decreased. And, of course, that's exactly what we saw happen. The high spin rates of the drink bottle and the Explorer 1 did begin to slow down, and the rotation rate diminish. Now, the one other thing to keep in mind as omega decreased is that the angular momentum L must still have been kept a constant, so that when this went down, in order to hold the momentum constant, the moment of inertia I had to increase, which meant that the drink bottle and the satellite did not spin any longer about their minimum inertia axis, but instead began to tumble and spin about its maximum inertia axis. In fact, its final stable condition was a spin about its maximum inertia axis at the minimum velocity, which was consistent with providing the required amount of angular momentum, and one in which there was no longer any turbulence generated so that Q could no longer increase. Returning to the story of the early Explorer satellites, I should tell you that the flexible antennas on Explorer 1 were replaced with nearly rigid ones on Explorer 2. Something like the antennas you see here on a small lunar satellite released by Apollo 15. So while Explorer 1 started tumbling in the first 90-minute orbit, it was many days before Explorer 2 did likewise. I hope you have gotten a little better feeling for the laws of motion governing spinning and tumbling bodies in space, and that you will be stimulated to try and understand some of our final examples.